next guest I'm really honored to present is my my longtime friend who says he's not a washed-up NOLS instructor, but here's his bio. Ian McCammon has degrees in physics, material science, and mechanical engineering, and he's worked in a variety of fields. Yeah, a variety of fields. Outstanding in the field. He's also guided and taught in mountaineering winter and whitewater expedition settings. If you're wondering what those various fields might have been besides the mountains, ask him what this means. He recently retired from the defense sector. So we're really thrilled that Ian McCammon has time now to apply his prodigious brain power back to the avalanche world. And so here he's going to talk to us about measuring slope angles. Ian, welcome. Hearty welcome, buddy.
Wow, thank you for the introduction, Lynn. Yeah, it's such an honor to be here with everybody. To be able to, it's been a while since I've been in Jackson, so it's really nice to come back and kind of reconnect with a lot of folks I haven't seen for a while. Some of the people in the AAA, so I'm going to do this really quick for Jane. So, yeah, Jane and Jen, thanks. Said they wanted people to wear these, so there you go. Great organization. If you're not a member, they have a booth here, so go check it out. You don't have to be a professional. It's a cornucopia of information if you're a backcountry skier or if you want to connect with other people in the avalanche community. It's great. All right, today I'm going to talk about slope angle. This is a bit of an adult conversation because we all know that there's more to decision making than slope angle, right? But we do know that slope steepness is a key factor in managing our avalanche risk in the backcountry. I know most of you are probably well-educated, you're smart, you have a lot of backcountry experience, but there are people out there maybe just coming out of avalanche, their Avalanche 1, or thinking about taking an Avalanche 1. And they might be wondering, well, how good are my measurements with an inclinometer? So let me start with a question. How many folks out there have used an inclinometer to measure slope angle? Yeah, don't be shy. Okay, yeah, looks like most of the folks. Great. There's a bunch of them out there. So you're familiar with this question. You're out there, and let's say the avalanche forecast says something like, the danger is considerable today, so we recommend avoiding slopes steeper than about 35 degrees. How many of you have heard statements like that? Yeah, pretty much most of us. So how well can we measure that 35 degrees? If we all went out into the backcountry and measured, found a 35-degree slope and measured it, how many of us would get the right answer? And even more important, if you're out there with your buddies, you're trying to make a decision about a slope to ski, does that mean a 34 is going to be okay? A 33, 32? How do you know? Well, what I hope you walk away from this presentation is some insights into how to make decisions in the face of that uncertainty. Okay. To answer this question, we really got to look at slope angles in three different things. There's three parts of this. The first is inclinometers. How accurate are these babies, really? And if they have inaccuracies, what does that mean for our risk-taking in avalanche terrain? What does that error translate to? And then finally, how do us as humans use that information to make decisions? Let's start with inclinometers. I know what you're saying. You're like, yeah, inclinometers. I don't use those because I got this cool app on my phone that's got colors on it. It tells me how steep the slopes really are. So yeah, I don't measure slopes anymore. I just follow this. Well, how accurate are those? This is a much longer discussion, but the current best available for normal people like us is the USGS program, the three-dimensional elevation program. They're using LiDAR and interferometer and a bunch of space-based things to come up with really good mapping of the surface of the Earth, especially the U.S. They've got most of the U.S. done, still some areas that are missed out, but studies of these show that these are really good on flat terrain. They give you very accurate results. But when you have trees present, when you have steep slopes, and then if you saw Zach Miller's presentation yesterday, you saw that, holy cow, when there's snow on a terrain and the map is telling you what the terrain looks like, but in reality, there's snow on top of that, that may not be a very good representation of what's going on there. So they're still doing research. This area is developing, it's getting better, but what the research says is that our slope angles generally can't be any better than 6 degrees. They're probably worse, especially at the edges of the color boundaries. So if you're saying, okay, well, this area is, I'm glad I'm getting some nods from the smart people. If you're saying, okay, the blue dot is right here, and if we stay just to the edge of this red area, we'll be okay. I'd say that's probably not good decision making. What this tells us is that these tools are important for route planning, but when you get out there, there's no substitute for actually measuring your slope angles. Okay, I'm moving right along. There's a bunch of other mechanisms out there. There's these things where a little ball bearing moves in a track. There's my favorite, compasses. There's your cell phone, a whole bunch of great apps for that. There's those dangly things, you get a string, and then Lifelink, RIP on that one, and then a whole bunch of other mechanisms out there. So the question is, how good are these? What's the best one, right? To answer that, I wanted to know the answer to that question, so I showed this at a bunch of my Avalanche courses. It's a pretty simple diagram. I asked people to measure the slope with their slope angle. So people were, with their inclinometer. So people were there, take an Avalanche course, they had inclinometers, their favorite ones. So I said, go ahead and measure the angle. But the two caveats, first of all, stand perpendicular to the screen. Because if you look at it off axis, you end up getting these weird parallax errors. So I had everybody stand up and stand perpendicular on a line parallel with that cross. And I also said, don't say it out loud. Write it on a piece of paper and hand that in, because I didn't want people getting influenced by what the person before them measured. Obviously, these are ideal conditions. This isn't the real world. But I wanted to find out, well, okay, under ideal conditions, best possible conditions, my feet aren't cold, I'm in the classroom, I've got my favorite inclinometer, all the time in the world to measure this. How good are we? Well, before we can find out, we've got to do a little bit of review. My apologies if this brings back any PTSD about high school science class. But when you make a repeated measurement, what you end up with is this bell curve. The group average is usually considered what's to be about the true measurement, but you'll find that you end up with these numbers on either side of that measurement, maybe a little bit high, maybe a little bit low. These typically follow a bell curve. Three kinds of error that can occur. The first is this random error. It's that spread around that central value. That's often called the measurement uncertainty. So you'll see measurements, say in temperature, expressed as plus or minus. So this is 42 degrees plus or minus 5 degrees, something like that. The second kind of error is gross error. So these are outliers. These are data points that really statistically have no business being outside of your bell curve. They are there because they indicate something went wrong with the measurement. Either the device itself was defective or damaged, the person copied the number down wrong, or they had some transcription error. That's a second kind of error, often called a gross error. The last is when you have a set of measurements, usually just say it's from a particular kind of device that doesn't match all your other measurements. You see the bell curve, but the whole thing is displaced to one side or the other. That's called a systematic error. In other words, there's something wrong with that particular device. Or maybe it's a person doing that. Okay, so three kinds of error. Let's see what happens. I got excited when I saw this because this is the data. I had never seen this before. As far as I know, nobody had ever done this before, so I was pretty excited to see it. You can see across the top, those are the different mechanisms of inclinometers. On the vertical axis there, you can see how far the measurement, each one of those black points, deviates from the subgroup mean. Okay, so that's what I'm interested in. So this, in other words, it doesn't matter if people were looking at, in one course, an image that was slightly tilted. All I'm doing is measuring the deviation from the average. So you see a couple of things here. Well, you see three things, the three kinds of error. Especially for the compass there, you see that spread. Check out what the spread is over. I mean, that's covering easily 8 degrees. Holy cow. So you could see the measurement uncertainty there. You can also see those empty circles are outliers. Something went wrong with the measurement. Either the device wasn't adjusted properly, it was manufactured incorrectly, or somebody made a mistake. The last thing you can see is if you look over to the string inclinometers, which we all know, the kind of Genghis, those appear to be biased so that they underestimate the slope angle by about 1 degree. But let's see if we can compare these. We'll summarize the data, and that's what this table does. So you got the gross error rate. That's how people made mistakes. There's the bias. You can see that's statistically significant since it's less than 0.05. So string inclinometers do in fact suck. And then you've got measurement uncertainty. And if you weren't sure about those string inclinometers, just check that out. The 95% confidence interval is 5.7. That means if you make a measurement with a string inclinometer, it's somewhere in an 11.4 degree range. Wow. Okay, let's say, oh no, I think the phones, these are the best. They're super accurate. They give me slope angles in a tenth of a degree, so they got to be accurate. You check it out, 3 point, plus or minus 3 point. That means your measurement is good somewhere within 6.4 degrees. Oof. Okay, let's this is a little bit sobering. And this is ideal conditions, remember, ideal conditions. So if I want to know how well we all do, what I did was I took the most common, which are these three, and I constructed an error model. And this is a different way to look at that error model. So what you're looking at here is the percent of measurements versus the accuracy window. So as you think about it, as your accuracy window grows, more and more measurements will fit inside there. So for instance, if you say, where's the 95% of my measurements will fall within what window? Well, you say, you look up here, you say, oh, 95, you read straight across, and you say, oh, okay, 95, that's a 7.8 degree window. Remember, that's plus or minus 3.9 degrees. So if you wanted 95% or 19 out of 20 of your measurements to be correct for a slope angle under ideal conditions, your inclinometer would look like the blue scale, where each interval was 7.8 degrees. Wow. Okay, now let's say you're like, yeah, listen, Ian, I don't, 95% or whatever. I just want to be right most of the time. So what's most of the time? Let's say 2 out of 3 times I want to be right. Oh, okay, well, 2 out of 3, that's about 67%. We can read off of this exactly what that is. So 67% is a 4 degree window. So that's 2 out of 3 of your measurements are only going to be accurate under ideal conditions in a 4 degree window. So let's get back to the question we asked originally. How many people get the right answer, an accurate answer, when you're measuring a slope angle in the field? Well, the answer's right here. We can check that out. So if we want to say, all right, how many people get within a degree of the right answer? That means the window's 1 degree, so the accuracy window is plus or minus a half. Okay, and here we go. Oof. Only 1 in 5 of my measurements under ideal conditions is going to be accurate. And is that sobering to anybody? I know it was for me. And I felt pretty bad about that. I had to double check my results until I realized that 1 degree is pretty dang small. And what we're doing here is nobody's fault. It's not the fault of the manufacturers. It's not our fault as people not measuring things rightly. These are fundamental properties of the thing we're trying to measure. This is inescapable. So if we're going to understand what this error means in avalanche terrain, we got to bring in avalanches. Let's see, how am I doing on time?
6 minutes left.
Okay, perfect. We got to understand avalanches. So how many folks have seen charts like this? You got start zone steepness versus number of accidents, right? And people familiar with this? Seen this before? Yeah, almost every avalanche book, every avalanche course covers something like this. But we're all adults here, and I told you this is going to be an adult presentation. So I'm going to let you in on a dirty little secret about these charts. You'll notice that these charts, whenever they're presented, almost, I can only think of one exception, almost without exception, the intervals are 3 degrees, 4 degrees, 5 degrees. That's the width of those bars you see going. And I don't know if you always wonder, like, why don't they just show it in 1 degree intervals? Here's why. This is what that data looks like. This is measured data, okay? So the data is way too rough, right? For 436 data points, that should be a much smoother curve. Something's going wrong there, and you start to stare at it and you realize what really is going wrong. This is the dirty secret. Check this out. The spikes exist at 30, 35, 40, 45, and 50. These are called preferred digits. This phenomenon is called heaping. It exists when the unit that you're trying to measure is smaller than the thing that you're trying to measure, the phenomena that you're trying to measure. So what you end up doing is unconsciously going, oh man, I don't know, it looks like it's around 35, and your brain automatically chooses these preferred digits. It happens in a lot of different areas. Fortunately, there's ways to fix this statistically and make some estimates. And that's what we do here, because we want to see what that error is going to do in avalanche terrain. So we end up with this familiar, this is a cumulative diagram of start zone steepness versus post-release frequency. So when an avalanche happens, how much of the time is it going to involve that slope angle? But wait, you say, avalanches don't just happen at one slope angle. They pull into shallower terrain. How often does that happen? Well, here's what the data says. I was able to find good data in 180 different accidents. Most of the time in these accidents, it pulled into terrain that was 5, 6 degrees steeper. But there were certain circumstances where those slabs pulled into much shallower terrain, by as much as 10, 11, 12, 15 degrees in some cases, about 5% of the cases. You can see I have the line there. That typically happens when you got persistent weak layers. You guys know, persistent weak layers, hard slabs, deep slabs. Those are the most common situations where it pulls into those unexpectedly shallow angles and can surprise you. So if we're going to talk about what is our error, when does it keep us out of trouble, we got to include this. So let's put our error in there, right? This is the error for our community model based on those 3 different kinds of inclinometers. That's what it looks like. So the numbers, the black numbers there are, remember this is our 95% interval. So that means, okay, if we got 95%, if we got 40 people measuring a slope on their inclinometer, it says 20 degrees. Every one of those 40 people got an inclinometer reading of 20 degrees. 38 of them will be in that window, right? That's 95%. 8 of them will have gotten it right? That what they read on their inclinometer was actually the slope, the slope angle. We're worried about the ones on the right, those 15 folks on the right, because their inclinometer said 20 degrees, but the slope under ideal conditions was actually 22, 23, maybe even 24 degrees. It's really quiet. I'm trying to read this. Are people shocked? Are they bored? I was sort of surprised at these results. All right, moving right along. That window is so big that if we had to divide this risk space into different intervals, how many intervals could we do? Well, I mean, you can kind of see it. It tells you right there. We can't divide this into any more than 3 intervals, because it's just simply the raw error. So what we see is on the left-hand side, 0 to 20 degrees, that's where our measurement error is not going to have an impact on our risk. On the other end, 30 degrees plus, then it is going to have a substantial impact on our risk. Well, Let's bring humans into it. How do we make decisions in this setting? People who study how folks manage risk have found that we generally go through 5 stages. We start with simple rules, and then we work into, just tell me the rules I need to be safe in avalanche terrain, right? And then we say, well, conditional rules. What are the circumstances I need to be aware of in avalanche terrain? And then we learn into understanding that cues, some of these things are more important than others. And then eventually we start to recognize patterns and eventually exceptions to those patterns. This is the expertise model, how you develop expertise. You guys can see that this maps pretty well. If you want simple rules in avalanche terrain, you really can't, regarding slope angle, you really shouldn't go above 20. Simple rules don't really apply. Once you get into red terrain, you need to be using much more complicated decision strategies. And I won't go into those, but that's what you learn in the level 1. Snowpack terrain, weather, how do they come together? A friend of mine said, if your decision are quick and easy, you're doing it wrong. If you're making decisions by simple rules, like, oh, I skied this last week and it's fine. I've never seen this avalanche. You know, there's a group coming right up behind us, and if we don't go now, we're gonna miss out, right? If you find yourself making simple rules, my ski partner says, it's like bringing a squirt gun to a knife fight. You're using the wrong tool for a very dangerous situation. How do you apply this? One thing you can do is eliminate the error in your inclinometer. Get to know your inclinometer. Find a piece of cardboard, measure up 4 or 6 inches along one edge, and then cut a diagonal that's exactly twice that. You're going to end up with a piece of cardboard that looks like this. And this angle is exactly 30 degrees. So how you use this is you can go to Walmart, get yourself one of these levels for about $3. Find a level surface, check it both directions. Once you got your level surface, you can measure your inclinometer and just make sure that that says 30 degrees. You may be surprised at what it tells you. And right on the back, what the error is. So just say, add 2 degrees, add 1 degree. And that'll help you understand if there's error in your inclinometer, that you can compensate for that. And yeah, you can reduce, but you can't eliminate your measurement error because there's natural variability. All right, check your decision making. So you measure a slope, says 36 degrees. You know there's error in your measurement, so it's much better to say, yeah, we're in the mid-30s. We're in the mid-30s. What does that mean? Well, it means we're over 30 degrees. So rather than spending our energy splitting hairs about whether it's a 32 or a 36 degree slope, let's do our homework. Let's be ready to answer hard questions about the snowpack, the terrain, the weather. Because that's how you're going to make decisions in that red area, not by splitting hairs. Okay, so yeah, avalanche courses are 4. So I'm going to end with a quote from somebody who I think knows a little bit about risk. He started one of the biggest investment firms, Warren Buffett. He said, it's better to be approximately right than precisely wrong. And with that, I'd like to say thank you to everybody. Thank you for having me here. Thank you for letting me present this research. Thank you to all the people that supported it. And there's a link to my ISSW paper.
You think we're going to let him off quite that easy?
Rats.
So in the first draft of your paper, you finished with a really good phrase that you might use with your touring group, using your error, your slope angle error understanding. With that in mind, do you know what the phrase I'm talking about?
I don't know what you're talking about.
You don't know what I'm talking about. Shit. Where you said something like, oh, you guys, this is so embarrassing. All right, since we're not very good at measuring slope angles, and the rest of the things out there are our avalanche forecast says this, our avalanche occurrences say this, then let's keep our touring today within these ranges. Do you remember
Yeah,
saying, do you remember, you
Yeah, I
wrote that, you wrote that.
Okay, all right.
Can you recap that? Because I thought that was
All right.
really important.
Okay, yeah, sorry. I guess I've written a lot of stuff and wrote that paper a while ago. Yeah, so anyway, Lynn is right on the nose. One of the motivations for this was two motivations, really. The first was students asking me what the slope angle was when we had all measured a slope, and there was a lot of variation. And they said, well, what's the real answer? And I said, well, it's this variation. And they said, well, what's the real answer? And I realized that as an avalanche educator, I had communicated the idea that slope angles have a specific, precise answer. And it took me a while to realize that, to do the science, but then now I understand that they don't have a precise answer, that there's uncertainty in our slope angle measurements. And as a result of that uncertainty, we got to look at a much bigger picture. We got to say, it's not just about the slope angle, it's about all those other things. It's about what's the avalanche problem today? Is it hard slabs? Is it persistent weak layers? Because that might pull into some shallower angles, and that error can get me into trouble. Is it recent wind loading? What about my terrain choices? Am I going to choose something that might get pulled? So I'm going to ski next to this bowl, but could that terrain get pulled and entrained in a slab? So you have to be aware of a much bigger picture. Is that
Yeah.
close enough? All right. Yes.
Hang on.
Oh,
We
gotta
get
get
to
the
use
box.
our toy. Here, Cronin. Take it back to Sophia.
While it's doing that, I just want to say these are preliminary results. I really hope somebody comes along and does some real-world measurements and some studies on actual slopes. Yeah.
Hello? Okay. I don't. Okay, so on the data,
Just if you talk into the box, they'll
on the data, it showed the number of accidents on the different measurement of the slope. We just walked through how we measure slope. So how is slope measured when they're recording accidents? Is it the same methods, or are they using different tools?
Thank you. Great idea. A great point. When I was collecting the data, I looked for accident investigations where the investigators actually visited the site and they reported the slope angle as measured, not estimated from a map, not estimated back in the office, but measured with an inclinometer in the standard accident reporting form. That I had access to for this research. There's a column where you enter specifics about the slope, and one of them is, what's the slope angle? How did you arrive at it? Was it a direct measurement on the slope with an inclinometer, or was it an estimate from a map? So in this case, these are all field estimates with one of these devices. Does that answer your question?
After an avalanche happened.
After an avalanche happens, yes.
So how do you measure the slope of the conditions if it's after an avalanche already happened?
Yeah, what you're measuring is the angle of the bed surface.
Okay.
Yeah, so, and granted, there's going to be differences. Like it's a big wind pillow, the slope error is going to be different for what the actual slope is versus what was left behind.
So even for the number of accidents, there's a margin of error.
Absolutely. Remember, this is under ideal conditions, right? So there's a whole lot of evils hidden in the real world. And what I wanted to do was start with a baseline of what is the best we can possibly do under ideal conditions. And then once we've done that, then we can start moving into those much more difficult questions. But I wanted the baseline.
Thank you.
Thank you for the question.
I'm gonna hook you up.
That's great. Thank you.
Oh, I guess we can give you one more.
You need the prop.
Yeah, well, we're not gonna chuck you the box, you're way up there, so Ian's gonna have to repeat the question.
Okay.
So this question is more about slope angle than measurement. There's a lot of skiers around here who routinely ski like double black diamond terrain in Avalanche
Wow, that is really not a short question. Yeah, so the question is, let's see if I get this right. This is about avalanche slope angle and avalanche frequency. It's a bell curve, right? And we always say it peaks around 38 degrees and starts to fall off. And so the idea is, oh, hey, if I'm skiing on stuff the far side, it's steeper, it's been sloughing, or whatever, that it's going to be safer because it's actually steeper. Is that accurate characterization of the question? Yeah, that's pretty complex. I don't think that terrain necessarily sloughs. Some of it does, but there are some things going on in the snowpack fracture mechanically that are fairly complex. I'm going to leave it at that. So I wouldn't hang my hat personally on, oh, this is a 42-degree slope, therefore it's safer than a 38-degree slope. I wouldn't go there because there's just not enough, there's too much error in the slope measurements to feel good about that decision. All right, I got to get out of here. Thank you, everybody.